On the morning of September 6, 1976, a Soviet Air Force lieutenant descended below radar coverage at near supersonic speed, crossed an international border without authorization, and landed at a civilian airport in northern Japan with 30 seconds of fuel remaining in his tanks. His name was Viktor Ivanovich Belenko. The aircraft was the Mikoyan Gurevich MiG-25P, NATO reporting name Foxbat. With that single act, Belenko handed Western intelligence the most significant technical windfall of the entire Cold War. What followed was not merely a diplomatic incident. It was a methodical, classified dismantling of the Soviet Union's most feared frontline interceptor, an aircraft that had shaped American fighter procurement policy for a decade, driven the design of the F-15 Eagle, and caused genuine alarm inside the Pentagon. For nearly 10 years, the West had built its air defense doctrine around an assumption of what the Foxbat was. On this day, the assumption was about to be replaced by the truth, and the truth, as it turned out, was both more reassuring and more unsettling than anyone had anticipated. The story begins not with the MiG-25, but with the aircraft it was designed to destroy. In the late 1950s, the United States was developing the North American XB-70 Valkyrie, a Mach 3 strategic bomber capable of cruising above 70,000 feet. The Soviet Air Defense Forces, the PVO, had no interceptor that could reach it. The Mikoyan Gurevich Design Bureau received the requirement. The prototype, designated Yi-155, first flew in 1964. By the time the production MiG-25 entered PVO service, the XB-70 had been canceled, but the Foxbat was already on the line, and Soviet leadership had found new uses for its speed. Western intelligence first observed the aircraft publicly at the 1967 Domodedovo Air Show. What analysts saw, or believed they saw, was a massive, twin-engined interceptor of formidable capability. CIA and DIA estimates credited it with a sustained top speed of Mach 3.2, a ceiling approaching 80,000 feet, and wing loading suggesting meaningful maneuverability. These assessments were, in several critical respects, profoundly wrong, but they were consequential. The fear of the Foxbat directly shaped the performance requirements for the McDonnell Douglas F-15 Eagle, an aircraft designed to defeat a threat that was never quite what the threat assessments described. Viktor Belenko was born in 1947. By his late 20s, he held a first-line assignment flying Foxbats from Chugayevka Air Base in Primorsky Krai, roughly 150 kilometers north of Vladivostok. He was, by all accounts, a skilled aviator, but his relationship with the system that had trained him had been deteriorating for years. The base was in chronic disrepair. Maintenance resources were inadequate. Attempts to raise these concerns through official channels were met with indifference. His marriage was failing, and the ideological confidence the Soviet system had tried to instill in him had been quietly eroding. Belenko later described obtaining American magazines and initially dismissing the consumer abundance depicted in them as CIA-fabricated propaganda, as he had been told. The gradual realization that those images might be genuine was, by his own account, deeply destabilizing. The decision to defect was not impulsive. Evidence gathered after the fact suggests Belenko had been planning for the better part of 18 months, studying navigational charts, identifying the right sortie profile, calculating the fuel mathematics for a crossing of the Sea of Japan. A solo low-level training flight would take him below ground radar coverage. On September 6th, that sortie was scheduled. He had made his decision. At the assigned moment during the exercise, Belenko did not pull up. He pushed the throttles of his two Tumansky R-15B-300 engines to military power, descended to an altitude below Soviet ground radar coverage, deactivated his transponder, and turned east. His unit's controllers began calling him on the radio. It was already too late. Fighters launched to investigate an assumed crash. The border guard report that an aircraft had crossed the state boundary toward Japan arrived too late to intercept. Belenko entered Japanese airspace and was met by Japan Air Self-Defense Force F-104J starfighters attempting to wave him toward Chitose Air Base. He continued south toward Hakodate, a civilian international airport, because his fuel state left him no alternative. The Tumansky engines at low altitude were consuming fuel at a rate his calculations had barely accounted for. At Hakodate, he set up a fast, hard approach, deployed the braking parachute on rollout, and brought the aircraft to rest with approximately 800 meters of runway remaining. He climbed onto the wing, fired his service pistol into the air to signal non-hostile intent, and announced his intention to defect to the United States. When the Foxbat stopped rolling, 30 seconds of fuel remained in the tanks. The margin between escape and catastrophe had been that thin. Before the aircraft had been properly secured at Hakodate, American and Japanese intelligence were already mobilizing. For nearly a decade, the Foxbat had been the subject of an enormous collection effort: signals intelligence, photographic reconnaissance, human reporting. And despite all of it, the Western picture was built substantially on inference. The prevailing assessment held that the MiG-25 was constructed primarily from titanium, matching the material choice of American Mach 3 programs like the SR-71 Blackbird. The assumed avionics architecture was transistorized or early integrated circuit, consistent with the miniaturization trajectory of Western aerospace electronics. The estimated maneuverability, based on wing plan form analysis and thrust projections, had led some analysts to conclude the Foxbat was a true multi-role fighter, capable of both high-altitude intercept and close-in air combat. These assessments were the foundation upon which the F-15 Eagle's design requirements had been written. They were not the product of incompetence. They were the product of the fundamental problem of military intelligence. In the absence of direct access, analysts fill the unknown with the most dangerous, plausible estimate. Every one of those assumptions was about to be tested against physical reality. And reality, it turned out, had a different answer on nearly every count. The diplomatic arrangement that gave the West access to the aircraft was a quiet masterpiece. The Soviets demanded immediate return. Tokyo and Washington produced a cover story. Landing gear damage made the Foxbat impossible to fly out. Transfer to the joint U.S.-Japanese facility at Chitose Air Base was required for disassembly and crating for sea shipment. Moscow accepted. 64 Japanese technical specialists joined American Air Force engineers for a systematic exploitation. Every major assembly was removed, measured, photographed, X-rayed, and sampled. The first major finding rewrote the threat assessment entirely. The MiG-25 was not built from titanium. It was built from steel, a tempered nickel-steel alloy comprising approximately 80% of the aircraft's structural weight. A further 11% was conventional aluminum alloy. Only 9% was titanium, reserved for the nose section and wing leading edges where thermal loads were highest. The structure was assembled by welding, spot welds, automated machine welds, and hand arc welds requiring skilled manual labor. This was not a backward design choice. Soviet factories in the 1960s could not produce titanium at the scale required for a production aircraft of the Foxbat's size. Nickel-steel alloy offered equivalent heat resistance, used tooling already available across Soviet industry, and cost a fraction of titanium per kilogram. The weight penalty was deliberate and accepted. At 29,000 kilograms empty, the MiG-25 was extraordinarily heavy, but it was never designed to dogfight. It was designed to accelerate, climb, and kill from a distance. The Temansky R-15B 300 turbojet engines were the heart of the Foxbat's performance capability and the subject of one of the most operationally significant findings of the entire exploitation. Each engine produced approximately 73.5 kilonewtons of dry thrust and approximately 100 kilonewtons in full afterburner. These were not refined high-bypass turbofan designs. They were large, single-spool turbojets built for raw thrust and thermal tolerance above all other considerations. At Mach 2.83, the aircraft's true operational speed limit, the engines were operating near the edge of their design envelope. Soviet test pilots had demonstrated Mach 3.2 in brief runs, but those flights required complete engine replacement afterward. The R-15B 300 was not a sustainable Mach 3 engine. It was a sprint engine. The fuel consumption at combat power profiles gave the MiG-25 an operational combat radius of roughly 300 kilometers from base. This was a critical revelation. Western assessments had assumed far greater operational flexibility. The Foxbat had been designed and optimized for one specific mission profile: scramble, climb at maximum power, intercept a high-altitude target within a narrow radius, and recover to base. Beyond that envelope, it was operating outside its design assumptions. The SR-71 had always been safe. The geometry never allowed a successful intercept. If the steel airframe had been a surprise, the avionics were a shock and would prove to be the most analytically significant discovery of the entire exploitation. When American engineers opened the nose and accessed the avionics bays of Belenko's aircraft, they found not miniaturized solid-state electronics, but rows of vacuum tubes, thermionic valves, the same fundamental technology that had powered radar systems in the Second World War. The initial reaction, reportedly, included laughter. This, some engineers assumed, was evidence of profound Soviet technological backwardness. That interpretation was wrong, consequentially, embarrassingly wrong. The radar was the RP-25 Smerch-A, NATO codename Foxfire. It was a large, powerful system with a detection range against bomber-class targets of approximately 100 kilometers, and it was built on vacuum tubes for two specific, deliberate engineering reasons. First, raw transmitted power. The Smerch-A was designed to burn through heavy electronic jamming from NATO's most capable EW platforms. Achieving that required a peak transmitted power of approximately 600 kilowatts. No transistorized radar of the era could generate that power level in the available space and weight. Vacuum tubes could. Second, electromagnetic pulse hardness. Any aircraft designed for nuclear war operations must survive the EMP environment that nuclear detonations produce. Transistor junctions are destroyed by EMP in microseconds. Vacuum tubes are inherently immune, no semiconductor junction to burn out. When American engineers subjected the Smerch-A to EMP testing, it survived pulse field strengths that destroyed American solid-state radar systems outright. EMP hardening became a mandatory requirement for all U.S. tactical aircraft avionics from 1980 onward, a direct consequence of what was found in Belenko's cockpit. Heavy, diplomatic, and consequential. The aircraft itself was an intelligence prize of the first order, but Victor Belenko was arguably of equal value. His debriefing covered not only the MiG-25's technical characteristics, but the operational doctrine, readiness posture, and limitations of the PVO in the Far East. Some of what he reported confirmed what Western analysts had suspected. He confirmed that the MiG-25 had never successfully intercepted an SR-71 Blackbird. The Blackbird, operating above 80,000 feet at speeds the Foxbat could not sustain without destroying its engines, had been a source of continuous frustration within the PVO. The R-40 missiles carried by the MiG-25P, large radar-guided and infrared homing weapons sized for bomber intercepts, were not adequate for the geometry presented by a Mach 3.2 target at extreme altitude. Belenko also described conditions at Chuguyevka: chronic maintenance shortfalls, personnel problems, resource failures that indicated the frontline PVO in the Far East was significantly less capable than its official posture suggested. And he provided information confirming that Western intelligence already had prior knowledge of the MiG-25's follow-on variant, then in development. That revelation sent alarm signals through the Soviet Ministry of Defense about the depth of the penetration that had occurred at multiple levels of the program. On November 15, 1976, 10 weeks after Belenko's landing, the disassembled MiG-25 was loaded aboard the Soviet cargo vessel Taiganos at a Japanese port and shipped to Vladivostok. The Soviets received their aircraft back in crates with every component accounted for. The forensic evidence of Western exploitation was extensive. Foreign-sourced fuses and resistors installed in the Smerch-A radar set were among the more visible markers. Infrared data from the engines running at full military power had been captured, critical for the development of heat-seeking missiles optimized against this target class. The structural materials had been sampled and analyzed. Every major assembly was now documented in Western intelligence files. The Soviet response operated at multiple levels. Those responsible, from base commanders to ideological supervision officers, faced severe consequences. The MiG-25 program itself was substantially redesigned into the MiG-25 PD Foxbat E, incorporating the new Sapphire-25 pulse Doppler radar with genuine look-down, shoot-down capability, updated engines, and revised avionics architecture. A direct, acknowledged response to the vulnerabilities the defection had exposed. The broader security review that followed within the Soviet Ministry of Defense was comprehensive and long overdue. The cost of one pilot's decision had proven, in strategic terms, effectively incalculable. The legacy of September 6, 1976, operates simultaneously at several levels. At the technical level, three areas were directly transformed. First, air-to-air missile development was accelerated by precise infrared spectral data from the R-15B300's exhaust plume, allowing seeker head designers to optimize guidance algorithms against this specific target class. Second, the mandatory introduction of EMP hardening across the U.S. tactical aircraft inventory from 1980 represented a fundamental change in American military electronics philosophy, driven entirely by what engineers had found in Belenko's avionics bay. Third, the confirmed performance characteristics of the MiG-25, its true speed limit, its modest structural G limit of 5G, its limited combat radius, allowed a recalibration of the threat envelope against which the F-15 had been designed. The Foxbat was not the multi-role superfighter the assessments had feared. It was a superb, specialized interceptor operating within carefully defined parameters. At the strategic level, the defection exposed something broader, that a decade of Western threat assessment had been inflating Soviet capability by projecting the most dangerous plausible interpretation onto insufficient data. The aircraft that succeeded the MiG-25, the MiG-31 Foxhound, entering service in 1981 with a true phased array look-down radar, addressed the Foxbat's documented limitations directly. It was a machine built from the lessons of this event. The MiG-25 Foxbat was exactly what it had been designed to be, and nothing more. It was built not from titanium and transistors, but from welded steel and vacuum tubes, materials chosen because they solved the actual engineering problems that needed solving within the real constraints of Soviet industry in the 1960s. The intelligence failure that surrounded it was not a failure of capability. It was the unavoidable consequence of the fundamental problem of military intelligence. In the absence of direct knowledge, analysts fill the void with the most dangerous plausible estimate. Victor Belenko resolved that ambiguity in the most definitive manner possible. And in doing so, he gave the Western world what a decade of collection had failed to provide, the unambiguous, physical truth of what was inside the machine they feared. That truth was more reassuring in some dimensions, and more sobering in others. More reassuring, the Foxbat was not the superfighter the threat assessment described. More sobering, what it actually was, an aircraft designed from the ground up to survive and operate in a nuclear war environment, said something important about the strategic mind of the people who built it. That is not a lesson serious students of military history forget.